So let's now extend our ideas of reciprocal space or K-space into 2 or 3 dimensions. Again, we're going to need gradient coils to do that. We'll need more than 1 gradient coil, we're going to need 2 or 3. And that means that our gradient can be represented as a vector depending upon the direction of the gradient applied by each individual coil. So we write this gradient vector as the gradient of the additional magnetic field that's applied by our set of coils. So how do we write that Larmor precession equation in this case? It's really exactly the same as before, as we saw it in 1 dimension. We start off with the precession due to the main static field, and then in addition to that we have another term due to the magnetic field gradient. But here we have to represent this in a multidimensional way. So we have a dot product between the gradient vector and the position vector representing that particular nuclear spin magnetization. Let's look at the pulse sequence that we would use with a normal time course of events starting with a 90-degree pulse and seeing how things evolve with time when we're using 2 or 3-dimensional gradients. Again, the same idea of a helix of phase wound up, which gets a pitch which is shorter and shorter with time, the wavelength decreasing, the wave vector or K-space value increasing with time. Now we write K-space as a vector relating to the vector of magnetic field gradient. It's a product of the field gradient vector and time. And of course the signal we acquire at any particular time is, as before, this Fourier relationship between the signal in K-space and the spin density now represented at particular positions in 2 or 3 dimensions. Again with the phase factors involving a dot product of the wave vector K and the position vector R. Here's an example of a 2-dimensional image. It's actually an image of my head taken in one particular slice through my head. So often in magnetic resonance we are dealing with 2-dimensional representations of data. And so let's look at how we might perform an experiment with a real pulse sequence that enables us to acquire a 2-dimensional image. Let's look at the way the pulse sequence works. We start with a 90-degree pulse. And now we're going to acquire our signal in reciprocal space, in K-space. But it's going to be 2 dimensions of K-space. So instead of being a single line of acquisition, we're going to have multiple lines represented here by a matrix of points. And at each of these points, we need to acquire the signal that will enable us to get a full 2-dimensional representation of the signal in the 2 dimensions of K-space. What we're going to do now is to carry out a traverse through K-space. We're going to look at a way of describing the history of what the spins do with time under the application of magnetic field gradient pulses. Here I've labelled a y-axis and an x-axis, and we're going to start off with applying a magnetic field gradient as a pulse along the y-axis. Here we see this pulse here. What has it done? It's lifted us up to some particular position along the y-axis in K-space. But at the same time, we could have applied a gradient in another direction along the x-axis. And here I've shown a pulse that has just the right amount of area to move us out to the very edge of K-space along the x-axis. So the combination of these 2 gradients take us to a particular line and a particular position at the edge of K-space. Here's where we bring in the spin echo to help us. The spin echo trick is just what we need here to flip us over to the left-hand side. We'll see in a moment why that turns out to be so useful. The spin echo, of course, involves a 180-degree pulse of the oscillating transverse magnetic field. And it has the effect of inverting all the phases of the spins. So that what that means is that the particular position we have in K-space is inverted through the origin back to the other side as shown by this blue vector. And now at this particular point in the pulse sequence we are ready to obtain our signal, and we're going to do so under the application of another gradient in the x direction. So here we go. We've applied the gradient in the x direction, and with increasing time we traverse across to greater and greater values of k, from the negative side through 0 to the positive side. And at each individual point along that line we acquire a signal, and we lay it down in the computer in our matrix for the signal at that particular point in K-space. That's how we get one line of our matrix. Of course, what we need to do is to fill that matrix up to get points along every single line of K-space. So we need to repeat the experiment. And we repeat the experiment using different values of the magnetic field gradient along the y-axis. By having different areas of pulse here, some negative, some positive, we can move our way to different lines of the K-space along the y-axis at will. That is the way we are able to fill the matrix. We give particular names to these gradient pulses. This one that moves us to different lines before we acquire our signal is known as a phase encoding gradient. Whereas the gradient we apply when we read out the signal along the line of this matrix here is known as a read gradient. And of course, under that read gradient, we're acquiring the spin echo. As the spins come into phase, as we go through zero value of k in the x direction and get out of phase again as we move past. There's that expression for the signal again. The signal is acquired in a two-dimensional matrix of K-space. The thing we want, of course, is the image in a two-dimensional matrix of real space. And so all we have to do is to take that signal and Fourier transform it in two dimensions. We perform a Cartesian Fourier transformation in two dimensions to get the image. What does that signal look like in K-space? Here on the left-hand panel we see a representation of that. It's a very strange looking signal. It doesn't look at all like an image, of course, because it's in the reciprocal space. In fact, it looks a little bit like a diffraction pattern. And these ideas of reciprocal space really lie at the heart of diffraction in all its forms. What's unique about magnetic resonance is that the way we acquire the signal enables us to make a direct transformation from the diffraction pattern to the image through this Fourier transform process. And so there we end up with something we recognise, the slice through my head. So to summarise, the process of magnetic resonance imaging involves a traverse through K-space where we acquire the signal at each of the points in K-space we need in either 2 or 3 dimensions. In the example I've shown you in 2 dimensions. That signal is then Fourier transformed to obtain the spin density image. Now with those basic ideas of K-space and the traverse through K-space, there's nothing about modern medical MRI that we can't understand. These are the key ideas. And what we're going to do next is an experiment on the Terra Nova where we'll perform an imaging experiment in 2 dimensions.